Alright, today's lesson is going to be on acids and bases. Technically, we're going to be looking at acid and base reactions. And actually, to be honest with you, we've already been doing these reactions. We just didn't necessarily call them acid-base reactions. We just kind of talked about them as reactions that form water. So when we have a double replacement reaction that has an acid and a base, what we're really going to be doing is forming water in these reactions. Okay? So we talked about acids in the previous chapter. And we talked about how to name the acids, and we talked about what an acid basically has inside of it, which is a hydrogen ion. Now keep in mind it's a molecular compound that contains a hydrogen ion, so it's kind of like an acid is kind of defying our properties of molecules, because remember, molecules equal no ions. So if we have a molecule, there's supposed to be, no ions. Okay, so no ions in a molecule, but an acid kind of conflicts with that. It conflicts with this notion of molecules. It's kind of like the middle ground between an ionic compound and a molecular compound. Okay. Now we talked about these before. You're going to see a hydrogen in the front of all of these, right? So when we talk about acids, we have a hydrogen in the front, and it's that hydrogen ion that makes our acid behave like an acid. One of the properties of acids, you should hopefully know, is that acids taste sour. So why do they taste sour? Because of this hydrogen ion. Now we're going to talk about acids and bases in a lot more depth in a later chapter, so I'm just kind of giving you a general overview right now. All right. Another property of acids is that they turn litmus paper red, and you've probably done something in like 7th, 8th grade where you dip litmus paper to identify if things were acids or bases. Okay, so that's our general idea of acids containing hydrogen ions. Our bases, now we haven't talked about these before, are ionic compounds. These are straight up 100% ionic compounds. There's no middle ground here. The key is that they contain hydroxide ions. Okay, so any base that we're going to deal with at this chapter is going to have a hydroxide ion. And again, in a later chapter, we'll talk about bases in more depth, and I'll talk more about how to identify them and getting into more details around them. Now, sodium hydroxide, again, OH, OH, and OH, each of these would be considered a base. Bases taste bitter, and they turn litmus paper blue. Okay, so they have opposite properties of an acid. All right, so if we look at acids and bases, obviously you know that the hydrogen ion and the hydroxide ion are going to come together to form the water molecule. All right, so let's take a look at this. All right, so acid-base reactions form water and a salt. Now, salt is a generic term for ionic compound. So anytime I'm talking about a salt, what I'm referring to is any ionic compound. Sodium chloride tends to be our most common salt because we call that table salt, but other salts could be things like potassium bromide, sodium iodide, anything that's an ionic compound, calcium, sulfate, these are all considered salts. Okay, so keep that in mind that an ionic compound and the word salt are interchangeable. So our acid, which tastes sour, reacts with our base, which tastes bitter, to create water, which has no flavor or no distinguishing tastes, and then a salt, which we know obviously has a salty taste to it. So what's happening with an acid and a base is the acid's properties are being removed by the base. So if I add these two together, I'm going to remove that acid property. Remember that acid property is based on the hydrogen ion, and our base property is based on hydroxide. So when I mix these two together and I make the HOH structure, which we call H2O, which is water, we remove the ions from solution because now we have a molecule. Remember I told you molecules are not going to be composed of ions. So we have a molecular species here that does not have ions that break off and cause electrical conductivity. All right, so remember that when we have an ionic compound, or in this case an acid that's aqueous, we would say that this is considered a strong electrolyte, right? And you'll hopefully remember what electrolytes are. Okay, and the reason why I'm bringing that up again is because if it's a strong electrolyte, that means it has ions in solution. So you got this hydrogen ion floating around in the water, and you've got a chloride ion floating around in water. Over here you've got a sodium ion due to the ionic compound, aqueous, again, strong electrolytes. Okay, and what's going to happen is these are going to join together. We're going to pour the two solutions together, and we're going to end up with our products. And what we'll have over here is sodium ions. So this will be aqueous. How do I know that? Because I know my solubility rules. All sodiums are always aqueous, and I'll have chloride ions in solution. But what I'll have also formed is molecular water. I'll have H2O in my container as well. Okay, so I've now formed the water molecule, and I've removed the hydrogen ions and the hydroxide ions. They're now locked in the water. So if I were to taste this, there would the sour flavor would be gone, the bitter flavor would be gone, and all I would be left with is a salty taste. Okay, so there's your general, acid-base reactions. We're going to follow the same rules we did for double replacement reactions. So if we're writing the reactions out, you've seen these already. So if I just do something like HNO3, nitric acid, reacting with, let's say barium hydroxide. Okay, so if I react these two together, you probably already know what to do here because you know to switch the ions, and you're going to end up with barium nitrate, which would be aqueous, and I would end up with water. Now, as I told you before, I like to keep water as HOH for these reactions because it makes it a little bit easier to balance. Alright, so if I have to balance the full reaction, okay, so all I did was I switched those two ions around with the barium with the nitrate, hydrogen with the hydroxide. So if I'm going to balance this, I'm going to balance my hydroxides first because I have two hydroxides. I'm going to put a 2 in front here to balance those two hydroxides, which means I then need two hydrogen ions, so therefore I have to put a 2 in front of here to get two hydrogen ions, which in turn means that I need two nitrates. Now I'm already noticing a little mistake I made, and this is okay. If you notice the mistakes, go back and fix them. I didn't balance the charge here. That should be balanced because barium is a +2 charge, and nitrate is a -1 charge. Okay, so I had to have two nitrates to balance the formula, so that's why I'm not putting a 2 in the front. Okay, so there's a complete balanced equation, but just like for the double replacement reactions that form a precipitate, we can do the same thing for acid-base reactions. We can write the net ionic version. So I can write the net ionic equation. Now the nice thing about these is because of the repetitiveness of our acid-base reactions, we're going to see the same reaction over and over and over again. Okay, so what I'm going to do is my spectator ions are the nitrate and the barium. Barium and the nitrate are my spectator ions. So what I have left over is the hydrogen ion, which is aqueous, and that reacts with a hydroxide ion, which is also aqueous, and I end up with HOH, or if you'd prefer, you could write water as H2O. Okay, and it's a liquid. Notice that I don't have aqueous here. I'm looking for things that don't form an aqueous. I'm looking for the formation of a solid, precipitate, or I'm looking for the formation of a liquid, which is water. Alright, now notice there's a 2 here for the hydrogen. Okay, I could draw that here, but I also have 2 for the hydroxide, so I should have 2 hydroxide ions, which I also form 2 waters. But I don't need to do that because I want to reduce it down to its lowest terms possible. And this is the net ionic equation for every acid-base reaction you're going to do in this chapter. Alright, so if you look at the practice problems we did in class, if you look at some in the homework, you'll see what I'm talking about a little bit more. But that is acid-base reactions. Thanks a lot, guys.